the chapter is about vector spaces. Okay. So, vector spaces. And we've discussed these ideas before, and perhaps it would help to bring all of these ideas together and see how they come together and how they relate to each other. So there's ideas about span and linear independence and subspaces and basis and dimension. And all of these combine together. Okay, so yeah. Let's bring all of those ideas together. And so the idea was, let's suppose you have a vector space, and there were several axioms that denoted what a vector space was, but the idea is basically as follows, and it's best demonstrated in terms of examples. So you have a space and you have some vectors in it. You've defined what kind of vectors you have, but the only thing that is important is that you should be able to define scalar multiplication and vector addition. These are the most. So if you have a vector v, you should be able to do alpha times v, where alpha is some scalar. And vector addition means if you have some vectors v1 and v2, you should be able to add them v1 plus v2. And so all of these vectors should be part of this space, right? And so there are other axioms as well which say that there should be a zero vector, there should be a negative vector for every v, so on and so forth. But the basic idea is you should be able to get all linear combinations, right? So linear combinations are important. And what are linear combinations? Linear combinations are simply if you have v1 and v2, then a linear combination of v1 and v2 will make another vector v3, which is perhaps alpha 1 v1 plus alpha 2 v2, right? And these are vector spaces. So as an example, and we've done several examples, but let's mention them again. So as an example, you have the vector space of R2, and vectors in this space look like perhaps v can be x1, x2, and another vector u can be y1, y1, y2. And this is a nice space because you can visualize it using a two-dimensional graph. Then let's suppose you have the vector space R3, where each vector looks like x1, x2, x3, three components, and another vector could look perhaps like y1, y2, y3, right? And we could expand these ideas, and so even R3 is nice because you can visualize R3 as a three-dimensional graph, but other spaces are not going to be so nice, because as soon as the dimension becomes more than 3, it's difficult to visualize them. So Rn will just contain vectors of the form, let's just write this as v will be v1, v2, dot 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 vn, and u would be u1, u2, dot 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 un, right? And so these are some examples of vector spaces. There are other spaces that are not r to the power something, that is, they're not just vector matrices, 2x1 matrices, or just a list of some real numbers. You can perhaps have the set of R 2x2 matrices as well, and so a vector in this would be something like perhaps v11, v12, v21, v22, and u could be perhaps u11, u22, u12, u21, and u22. And you could also have the space B3 that we've discussed before, which is the polynomials of degree less than 3, which is basically a vector could look like v0 plus v1x plus v2x squared, so a quadratic polynomial. U could be perhaps u0 plus u1x plus u2x squared, and these are just some examples. You can have many vectors in a vector space. And similarly, the space of continuous functions from a to b, that also forms a space. So perhaps one vector could be simply u equals to some function which is continuous, perhaps x. Another vector v could be g of x, which is, let's suppose, takes the absolute value of x, and we know this is a continuous function, this is a continuous function. And perhaps another vector w could be h of x equals to x squared. We know that even this is a continuous function, right? And so these are some examples of vector spaces. And so at this point, let's talk about subspaces. So consider this vector space that you have. Let's suppose you have a vector space already, and you have some vector x1 and you have some vector x2. You already have two vectors. Let's suppose you take these two vectors, this is some vector space V, and now you start taking linear combinations of these vectors. So let's suppose you say v3 is going to be x1 plus x2, sorry, x3. x3 is going to be x1 plus x2, and now this is just a linear combination of these vectors, which means x3 is also going to be in this space. Let's say you take another combination, x4, x1 minus x2. You take another combination, 2 times x1 plus x2. You take another combination, x6 minus x1 plus 3x2. You could even take the 0 vector over here, so 0 vector would be 0 times x1 plus 0 times x2, and you get the 0 vector as well. And so if you take all possible combinations, so x4, x5, x6, so on, and if you combine them together, what you will see is that you get lots of vectors in this space. And what you've essentially got in yourself is, when you combine all of these linear combinations, then you've essentially gotten a subspace of your original vector space, right? By taking all the linear combinations of two vectors. And this is just an example of when you can create a subspace on your own. The key is, of course, that you have to take all possible linear combinations of the original vectors x1 and x2. If you don't include all possible linear combinations, it's not a subspace, right? And so a good question is to check, how do we check if, let's suppose, we have a vector space, right? Let's suppose we have a vector space and we are given some subset in it. I'm not calling it a subspace, I'm calling it a subset. So there was a vector space and you have been given this blue region which contains some vectors. Either they give you a list or they give you a formula on how these vectors have been collected. So let's suppose there are some vectors v in it, vi's in this space, and you're supposed to check. So let's suppose this is s and this is v, and you're asked the question, is s a subspace of v? And the answer to that is just to check if all possible linear combinations exist in X. Remember that when we created a subspace, we were taking all possible linear combinations. So if you have a subspace, you are going to ask the question, for every v, is alpha v in my subspace, that is a scalar multiplication? And if I have v1 and v2, is v1 plus v2 in S? In other words, you can just simply combine these together and ask the question, for every v1 and v2 in my subspace, is there linear combination alpha 1 v1 plus alpha 2 v2 in my subspace? And if there is some linear combination, let's suppose you pick up a vector from the space and you pick up a set of vectors from the space, take a linear combination, and if that linear combination is outside, then this is not a subspace. But if all possible linear combinations of the vectors inside it, all of them are also inside, then this is indeed a subspace. So you just need to make sure that no linear combination is outside the space. Everything needs to be inside, and that's how you check whether a subset is a subspace or not, right? So S is a subset right now, so this is a subset, but you need to check whether it's a subspace or not, okay? And so that's how subspaces are related. Okay, and so at this point the question arises, let's suppose I want to expand this subspace. So let's take, now we have a subspace, let's say we had a vector space V, and we were creating a subspace by we created a subspace by taking all possible linear combinations of x1 and x2, right? And now let's say I want to make this bigger, I want to expand this subspace, and so let's suppose I include another x3, right? Now the question is, if I take all possible linear combinations, so alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, question is, will my space get bigger or not? Because notice that if I have already, if my x3, let's say I want to take an x3 which is already here, if it's already here in this space, then my space is not going to get bigger. Because if x3 already belongs to S, let's call this S, then x3 can already be written as a linear combination of v1, x1 and x2. So x3 already exists in it. So if you start taking linear combinations of x1 and x2, that's not going to give you any more vectors. It's going to give you the vectors that are already here. And at this point, you will not get a new subspace. If you want to expand the subspace, you have to take a vector that's outside this space. And now you say, okay, if I start taking vectors out 1x4 outside, and so if I start making a subspace alpha 1 x1 plus alpha 2 x2 plus alpha 3 x4, and if you start taking these combinations, then you would have expanded your subspace. So your subspace will now perhaps look something like this. So you have more vectors now, and so let's call this S2 perhaps, S2, oops. So this is S1 and this is S2. And so let me restate that when you take x3, you are not getting a bigger space, because notice that if x3 is already in your space, then whenever you take alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, since x3 can already be expressed as a linear combination of x1 and x2, you don't have you don't have new vectors. You have essentially alpha 3 times, let's say a times x3. So let's make this, there's lots of alphas now, and so this might get confusing. So a times x1 plus b times x2. So ax3 ax1 plus bx2. Notice that now what you have is another linear combination. So if I write this as alpha 1 plus alpha 3a plus alpha 2 plus alpha 3b, this is again just a linear combination of x1 and x2. So if I wanted to expand my space, I can't take the same vector from the original space. I have to take some vector that is outside the space, and then I can make a bigger subspace out of it. And so this is the notion which comes up, which is basically of linear independence. So in the example that we just did, x1, x2 and x4 were linearly independent, but x1, x2 and x3 were not linearly independent, because x3 can be written as a linear combination of x1 and x2, and that's where linear independence comes in. And so notice, if you recall, you check whether they are linearly independent or not by doing the following. So if you have, let's suppose x3, if you have x3 as simply as ax1 plus bx2, that is x3 is already part of that subspace, then you have ax1 plus bx2 minus x3 is equals to 0. That there is some combination, there is some linear combination of these three vectors such that a is non-zero, b is non-zero, and there is another c which is equals to minus 1, and ax1 plus bx2 plus cx3 is 0. So if you recall the way we checked linear independence, the way we did, linear independence is actually stated as checking they are linearly independent if you take c1 x1 plus c2 x2 plus dot 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 cn xn. This should be equal to 0 if and only if all the ci's are equals to 0. That is c1 equals to c2 equals to dot 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 cn equals to 0. Because if they're not all 0, then you will have a situation like this that we had with x1 and x2 and x3. So that's where the idea of linear independence comes in, right? Okay, so that's the idea for linear independence, for subspaces, and for vector spaces. And so let's take this one step further. Let's expand it so much. Let's go back to this space and try to expand this subspace even further. Let's say I take another x5, let's suppose. So I take another x5, and the idea is I want to cover this entire I want to make the subspace so big that it covers this entire vector space. That is, when I take the linear combination with x5, I get all the remaining vectors in this space, right? And at this point, what you have is, if you have a set of vectors x1, x2, x3, x4 and x5, we have this set such that when I take a linear combination of all of these, linear combinations cover the entire space V. When a linear combination of all of these vectors covers the entire space, what we actually have is a basis. We call this a basis because now for every V in my vector space, I can write it as some combination of my basis plus alpha 3 x4 plus alpha 4 x5. So that's a basis. When you take a bunch of vectors such that taking all possible linear combinations of them will cover your entire space, if your entire space gets covered, then you have a basis for your space. And so this is where the idea comes from, that your basis set needs to be linearly independent, which we just saw in cases of x4 and x3, and the idea that it should be the span. It should span V. What's a span? Span is basically when you start taking linear combinations. So this entire space that you had was a span of x1 and x2, because you were taking all possible linear combinations of x1 and x2, right? Okay. And so that's a basis. So when you have your space covers the entire, your subspace covers the entire vector space, you have a basis for your vector space. Okay. All right. And so over here you have one idea that tells you that bases are not unique. So if you take x1, x2, let's suppose we had space V, and I started covering with x1, x2, x3, x4, this basis is not unique. I could even take some other set, u1, u2, u3, u4, and I can cover this. If I can cover it with these, there is possibly another basis set which can cover my entire space. So bases are not unique. You can take these 4 sets or these 4 vectors. Okay. How do we check if any set of vectors span a vector space? So we check. So question, how do we check that any set of vectors span a vector space? The idea is, of course, that if it has to span the entire space, then you should be able to take any vector V from your space, then you should be able to express it in terms of V, in terms of, let's say your collection is, you're talking about the span of x1, x2 and up until xn. Then you should be able to write V as alpha 1 x1 plus alpha 2 x2 plus dot 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 alpha n xn. And if you want to show that it spans the entire space, you need to solve for these alphas. Solve for alphas. Note that this has to be some general vector. So for example, let's take an example. If you wanted to show that you have some basis vector, let's say you have a collection, x1 is, okay, let's not write these vectors, let's just say x1 is some vector, x2 is some vector, and x3 is some vector. And let's suppose you're working in R3, your vector space is R3, okay, and so you just take some arbitrary vector from R3. So I take v from R3. Now if it's from R3, then of course it looks something like this: v1, v2, v3, okay, and you need to show that this is equals to sum alpha 1 x1 plus sum alpha 2 x2 plus sum alpha 3 x3, and you have to essentially solve for alphas, or solve for alpha 1, alpha 2, alpha 3 in terms of v1, v2 and v3. So you have to show that if this is v1, this is v2, v3, then I can find some alpha 1, some alpha 2 and some alpha 3. So you just have to solve this equation, right? So for example, if x1 was 1, 0, 0, this is just a trivial example, 0, 1, 0, and x3 was 0, 0, 1, then I can solve this equation by setting alpha 1 to, so if I have alpha 1, 1, 0, 0 plus alpha 2, 0, 1, 0 plus alpha 3, 0, 0, 1, then this just becomes very easy to do, because this equation is alpha 1, alpha 2, alpha 3, and on the left side you have v1, v2, v3. So the solution is simply alpha 1 is v1, alpha 2 is v2 and alpha 3 is v3. So you've solved for alphas in terms of v1s and v2 and v3. But this is of course very easy. This could be a little bit different if, let's suppose, this vector could be, let's suppose, 1, 0, 0, 1, 1, 0 and 1, 1, 1. In this case you will get some different alpha 1, alpha 2, alpha 3, but you have to solve it. Okay, perfect. So next up, so we have a basis, we have linear independence and blah blah blah, and so now let's talk about how these ideas are related to matrices, because at the end of the day we are really interested in stuff like AX or stuff like AX equals to B, and so what we're really interested in m by n matrices and how these relate to this, right? And so let's take an example where A is an m by n matrix, right? And so what you have is you have m rows and n columns, and now you can see that these m rows, let's talk about these rows first. So let's suppose row 1, row 2, dot dot dot, row m. Each of these RIs will have n components, right? Because there are n columns, so that means each of these RIs will be something like R11, RI1, RI2 up until RIN. So these rows will actually be members of Rn, right? And if you look at it in terms of columns, so if I look at in terms of columns, so let's suppose the column is C1, C2, dot dot dot, Cn, then these Ci's will have m entries, each of these entries, so first entry, second entry, third entry up until m entry. So these Ci's will be members of Rm, and so it helps to see that actually this matrix A is sort of a bridge. If you consider a vector space Rn, and if you consider a vector space Rm, so let's suppose if you're doing Ax equals to B, let's suppose you took a vector in this space X, and if you multiply it with A, this vector is of course n by 1. This is m by n, which means vector B is going to be in m by 1, which means if you take a vector x and if you multiply it with A, then what you have is essentially you're going from this space to this space, and if you multiply with A, what you get is a vector in the other space B. So by multiplying with A, right? And so let's look at it from this angle. So what you're doing is when you're multiplying vectors in this space by this matrix, you get vectors in this space. Now at this point we get a notion of some subspaces, and so firstly we have a subspace null space, and the idea is you ask the question which of these vectors in this space when multiplied by A. So let's make another diagram. We have Rn here and we have Rm here, and so I'm asking the question that if I multiply, which vectors will I multiply in this space which will give me a result of 0. So I'm solving, basically I'm asking what's the solution, the solutions of the homogeneous equation Ax equals to 0. And those solutions, let's say these solutions are perhaps x1, x2, some collection, right? So let's make some collection. And so let's suppose I make some collection here which is made up of x1, x2 and all of these x's, such that ax1 is equals to 0, ax2 equals to 0, and so on. And the idea is that this is a null space. These solutions is called the null space, and this null space actually forms, you will notice that if you take any linear combination of such vectors, so let's suppose x1 and x2 was there, x1 and x2 was there, and if I take a linear combination, let's say alpha x1 plus alpha x2, alpha 1 and alpha 2, and if I now multiply A with it, then notice what happens. Alpha 1 A times x1 plus alpha 2 A times x2. Ax1 is already 0 because it's in the null space. A times x2 is also 0. So any linear combination is also going to be in here. So this null space actually turns out to be a subspace. This is a subspace of Rn, which is interesting, right? Okay, let's look at some other spaces. Let's look at the row space. What's the row space? Row space is basically, again, write it as rows. So view the vector A, matrix A as rows R1 dot 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 Rm. These are R1 to Rm. If you start taking linear combinations of these, right? So basically if you start taking linear combinations, alpha 1 R1 plus alpha 2 R2 plus up until alpha m Rm, take some linear combinations of these vectors. Now notice that we said that these vectors, all of these vectors are in Rn, right? So this also forms. So, right, if you have your, this is Rn and this is Rm, and so the row space actually is another, if I make a combination, if I take all of these linear combinations, they're going to be in Rn. So actually the row space is also a subspace. So this contains all of the linear combinations of R1, R2 and so on, right? And so this row space is also a subspace. So a row space, this row space is a subspace of Rn, okay? All right, let's look at one more subspace and then we will talk about something important. Okay, so let's talk about the column space. The column space is actually made up by all linear combinations of the columns of A. right? So columns of A, just like I said before, columns of A are going to be in the row space Rm. So since we have these two vector spaces, Rn and Rm, columns are actually going to be in this space, so C1, C2 and so on. And if you start taking linear combinations of these, then again you have another subspace. You have another space, but this time the subspace is not in Rn, this subspace is in Rm, and so we have that the linear combinations, so alpha 1 C1 plus alpha 2 C2 and all of these forms, so the column space is a subspace of Rm, the m-dimensional real space. Okay, all right. And so let's wrap up this entire discussion by mentioning the rank nullity theorem, which ties all of these ideas together. So firstly, notice that when you have a basis, what's the dimension of a space? So let's talk about the dimension. When you have the basis for a vector, just like we did over here, we had 4 vectors as basis for this. Since we have 4 vectors that make the entire space in a way, so we say that the dimension of V is 4, because you just need 4 basis vectors. So the number of basis vectors that you need is just your dimension. And so similarly, we know that the dimension of Rn is n, and the dimension of Rm is m, because you need m basis vectors for this one and you need n basis vectors for this one. And so let's tie down this idea. The idea is as follows: the rank nullity theorem. The rank nullity theorem just says this interesting fact that if you take the dimensions of the row space, which is called rank, and if you, this is being talked about in terms of a m by n matrix, right? So if you take the dimensions of the row space and if you add the dimensions of the null space, right? So this is called the rank and this is called the nullity. If you add these two together, these should be equal to n, right? So rank plus nullity is equals to n, which is interesting in terms of these two pictures that I have drawn here. Let's take these two pictures and let's talk about the rank nullity theorem in terms of these pictures. And the idea is, let me just get rid of this. So if this, and let's just put this here. Okay. And so the idea is that if you have this null space and this row space, these were the two spaces that we were talking about. If you take the dimensions, इसके जितने भी dimensions हैं, let's suppose let's call that r, and इसके जितने भी dimensions हैं, when you add them together, what you get is n, r to the n, right? So these pictures are actually not correct. The correct picture is something like this. When you, if the dimensions of both of them combined forms the dimensions of the entire space, what you actually have is something like this, where part of the space forms the null space. This is null of A, and since when you combine the rank to this, so this is null space of A, when you combine the row space to it, you get an n-dimensional space. It essentially means that the rest of the vectors are sort of in the row space. So this is the row space of A, because when you combine their dimensions, you get the dimensions of Rn. right? And that's what the null space, the rank nullity theorem is essentially saying. That's how these ideas of linear independence and bases and null space, row space, these are all connected. Okay, so that's it for, and there are other interesting connections as well. So in chapter 4 we talk about linear transformations, and in chapter 5 we talk about orthogonality, and we have talked about some interesting ideas that, for example, that the row space, that the range of A, actually not the row space, the range of A is the orthogonal complement of the null space of A transpose, which is an interesting idea. So if A is the link between Rn to Rm, then A transpose is sort of the link from Rm to Rn, sort of going from here to here, right? And similarly, the range of A transpose is, you know, and the complement of this, the orthogonal complement of this. And so this is how these ideas are connected. Okay, that's it for today. Just a basic overview of what these ideas are and how these are connected.